We have just enough time for a brief introduction before Zvika starts his talk. So it's a great pleasure to introduce Zvika Brakerski. We'll speak about when the universe speaks in quantum crypto. Zvika is a professor at the Weizmann Institute of Science. He's made breakthrough contributions to the theory of cryptography in many different areas, very famously in the study of fully homomorphic encryption and quantum cryptography, also obfuscation, verifiable computing, and many more. He's a recipient of the Blavatnik Award for Young Scientists in Israel, of the Gödel Award, and the Fox Test of Time Award. And I'm sure I'm omitting some other awards from this list. So we're very lucky to have him. Looking forward to his talk. And without further ado, let's welcome Zvika.
Thanks, Guy. Hi, everyone. Well, thanks for being here. Thanks to the committee for inviting me and for the organizers for organizing this this great conference. I would like to start with some personal words. It was really hard for me to prepare this talk, and not because of the contents of the talk. As you may know, we had in my country, in Israel, there was a bit less than 2 months ago, an enemy invaded our country and literally sent death squads to murder families in their homes, and moreover declaring that they want to do it over and over again, no matter what. So that's very unsettling. So I made the talk. Hopefully it'll be educational and also entertaining. There's jokes and everything. But I do want, to remind there's still a cloud over this this whole thing. So I will start the talk now. Thanks for bearing with me. So the talk is going to be about quantum cryptography and the universe. So I'm going to start by talking about quantum cryptography. So quantum cryptography is doing pretty well. So TCC 2009 was my first TCC. And there was one quantum paper there out of 33 papers in the conference. This year I checked, I found 6 quantum papers out of 68. So both in number and in ratio, we're doing pretty well. And in crypto, there's a similar phenomenon. And in general, I feel like quantum computing is becoming bigger and more mainstream, both in the TCC and general theory of computer science communities. It used to be that when someone gave a talk about quantum computing, they'd have to spend time introducing the model and so forth. And at this point, I think most people sort of know at least the basic guidelines. Talking about my own personal experience, I took a class in quantum computing back in undergrad in 2001 with Dorit Aharonov, who actually sort of did a very good job at sort of giving us the right intuition or approach on how to think about quantum systems. So that was great. I'm not sure how much of the technical content I remembered, but still I felt that I knew what was going on. So I went to these, the quantum sessions that were like usually the last session in the conference and very low attendance, and tried to sort of figure out what was going on. And things are very different now. I think, things are much more mainstream. And you may wonder why. I don't really have an answer. You could guess that maybe it's related to the advances in actually constructing quantum computing devices, which gave rise to things like the NIST post-quantum cryptography competition, trying to construct cryptographic primitives that are resilient to quantum attacks. There's probably some feedback loop there. So that's probably something that brought quantum computing back more to the attention of people. I also think that maybe there's like a bunch of brilliant students that were looking for cool hard problems to work with. And quantum computing is like a great playground. It has a lot of interesting and important problems that sort of brilliant researchers can sink their teeth in. I should mention before moving on that most TCC and theory of computer science works in quantum computing still work in this model of fault-tolerant quantum computing or fully scalable quantum computing, which is not what the machines that are currently built are implementing. So there's still a way to go. So this is still sort of forward-looking research, and at least in terms of sort of being able to actually implement it. But nevertheless, these are sort of important problems. And I'm sort of coining this term quantum TCC to refer to those quantum questions that we, the TCC community, care about. So it's not necessarily papers that are published in TCC, but it's the papers that it's the problems that TCC people would care about. And in recent years, we've seen a lot of progress and multiple fronts on this quantum TCC. And I'm just going to sort of briefly go over a few of them, but the talk is going to be sort of very focused. But I didn't want to just go without mentioning them. So one thread is to work on post-quantum cryptography, which is classical cryptographic primitives that are secure against quantum attacks. So you can think about cryptographic assumptions, you can think about building blocks, you can think about proof systems or protocols. And there's a more basic question of how to model security in the presence of a quantum attacker. So for example, rewinding becomes an invalid technique, at least out of the box, and there are other challenges. So there's a lot of work that's done there, how to work in the random oracle model. The other thread I wanted to talk about was what happens when you actually want to use quantum communication. So protocols that actually use quantum communication. And again, you can ask all of the questions that we're asking in the classical world, also in this world where you're also allowed quantum resources. The third bullet here is something that actually has no real classical parallel, and that uses the properties of quantum states that they are unclonable. So we're going to talk about a little bit more later, but essentially you cannot generically copy a quantum state. And this means that you can actually use this property for cryptographic purposes. Most notably, quantum money relies on this unclonability property. There's works on quantum copy protection, certifiable deletion, all sorts of tasks that you sort of have no hope of doing in the standard classical model, but you can do quantumly. There's a thread of work on delegating quantum tasks. So this is the case where you have a classical party that wants to utilize a quantum party. So you want to delegate a quantum task while you yourself are classical. So there's questions of security and questions of privacy. So you can think about certifying quantum computation. You can think about certifying generation of randomness, which is a task that quantum devices know how to do. You can think about protecting your privacy in the process and so forth. And you can also think about the foundations of quantum cryptography. So all of those basic questions, what does it mean? What does one-wayness mean? What does pseudorandomness mean in a quantum world? This is also an area that has seen a lot of progress recently. But today, we're going to talk about quantum gravity, which is not exactly on this list. In particular, how cryptography comes up when thinking about the universe. And the way that I want to do this is by actually starting by talking about a few ideas from the foundations of quantum cryptography. This is also going to remind us a little bit of the model, and then I'm going to relate them to things that are going on in quantum gravity. So let's do it. Let's start by talking about quantum pseudorandomness. In particular, I want to talk about quantum pseudorandom states that were introduced by Ji Liu and Song. So the idea there is to create a pseudorandom quantum state. So let's start by talking about what quantum states are. So a quantum state, an n over n qubits, so an n-qubit quantum state, is defined by 2 to the n dimensional complex unit vector. So you can see it. Oh, let's try this. Good. Okay. So you can see that that phi here is a vector, and it has 2 to the n coordinates. It has 1 coordinate for every classical configuration. So we have n qubits, which is the sort of quantum system that corresponds to n classical bits. So for every configuration of n classical bits, we actually have a coordinate in this vector. And each of these coordinates has a coefficient. And so you have a 2 to the n dimensional complex vector here. And this is the quantum state. How about now? Good. I'll do both. So we said that it's a 2 to the n. Okay, that didn't work. So we said that it's a 2 to the n dimensional vector. So it contains a lot of information. It contains an exponential amount of information. But actually, this phi only contains n qubits. So you can only really extract n bits of information out of this. And perhaps sort of most famously, you can measure this quantum state in the standard basis. And then you're going to get as an outcome an n-bit classical string. And you're going to get the value x with probability that is the absolute value of cx squared. But there's other ways to process this quantum state, but you're still not going to be able to get more than n bits of information out of it. And so what does it even mean that it has an exponential amount of information if you can only extract n bits out of it? So really, if you want to extract, you can recover more information, but you need to have more copies of this quantum state. So instead of just giving you, n qubits containing this quantum state, I can sort of give that to you and then give you n additional qubits that store the exact same state. And I can do it again and again and give you t copies of this quantum state. And this will allow you to extract sort of t times n bits of information about this sort of exponentially long vector. So in that sense, the quantum state is sort of well-defined, even though you can only extract n bits out every time. So this sort of hints to two properties of quantum states. One is that information extraction is in general a destructive process. Otherwise, I could have sort of extracted n bits and then extracted a little bit more. But in general, that would destroy the state. And the second thing is what I alluded to before, is that quantum states cannot be, in general, duplicated. So there's this famous no-cloning theorem. And essentially, if you could, then you could have just, I could have given you one copy, and you could have copied it and extracted more information. So these are sort of basic properties of quantum states. Now, what is a random quantum state? Well, it's just taking this exponential dimensional vector to be uniform over the unit sphere. That's all. And that has a lot of entropy, like an infinite amount of entropy if you want to be most general. But even with finite precision, it has an exponential amount of entropy. And again, if I give you exponentially many copies of the state, then you can extract it. Now, what is a pseudorandom quantum state? So that's what you would think. It's a low entropy distribution, so it can be generated from a polynomial seed efficiently in such a way that the quantum state that you get is indistinguishable from uniform, even if you're given polynomially many copies of this quantum state. So it can be an adversarially chosen number of copies, so long as it's polynomial, and should still be indistinguishable from this other vector that has an exponential amount of entropy. Okay, so JLS, who sort of proposed this idea, had suggested quantum money as one motivation, and also that these pseudorandom states can model sort of the ground state of generic physical systems. They also showed a construction from one-way functions. So essentially, giving us the sort of construction from the weakest possible crypto assumption. Well, not so sure. So we're used to thinking of one-way functions as the weakest assumption that is necessary essentially for cryptography. And where's Iftach? So shout out for Iftach's talk 2 days ago. At least in most cases, we think that one-way functions are essential. And this was semi-formalized by Pagliazzo and Luby. So if this is the most basic cryptographic primitive, then is it implied by this notion of pseudorandom states? So it's enough to think about a little bit to figure out that probably not. These notions are sufficiently different that they should not, that pseudorandom state should not imply one-way functions. It's not so easy to prove, but it was proven using a quantum oracle separation by Kretschmer. So we know that at least in some formal sense, pseudorandom states are not expected to give us one-way functions. But what does this mean about the role of one-way functions as the minimal cryptographic assumption? Well, you could think that maybe pseudorandom states are not actually crypto, because if you think about the motivations that I mentioned in the previous slide, we talked about quantum money and sort of modeling quantum systems. So maybe pseudorandom states are only good for quantum tasks, and they cannot help us in getting classical cryptographic tasks. Turns out this is not the case, and actually you can do cool classical cryptography just with pseudorandom states, and this was shown very recently. My focus is going to be on bit commitments. Because quantum bit commitments are actually, very also classical, but quantum bit commitments are a very interesting primitive with many properties that supersede what is known classically. So, and they're very useful for many applications. So, in particular, in the quantum setting, you can take any commitment protocol and turn it to be completely non-interactive. So you can have you can even have non-interactive, statistically hiding commitments, which is something that is just not possible to do using just classical communication. It also implies a bunch of other other crypto primitives that we think of as being pretty strong, like oblivious transfer, which in the classical world is not implied by commitment schemes. You can also use, so what I'm talking about here is actually quantumly committing to a classical bit. So this is it's a classical task, and we're performing it using quantum resources. But you can also think about committing to quantum states, and you can also do this using classical commitments. So commitments are kind of cool. You can also show that in the quantum world, the existence of commitment schemes, of bit commitment schemes, are actually equivalent to this new primitive that we defined that we call EFI. And EFI is just a pair of distributions over quantum states, which are efficiently sampleable. They're statistically distinguishable, so they're statistically far, but they're computationally indistinguishable. So this is a very basic primitive. It's just distributions that are computationally indistinguishable, statistically far. In the classical world, this is equivalent to one-way functions. In the quantum world, this is equivalent to commitment schemes. And we don't know what is the relation to other primitives, but at this point in time, I think that we do not know of any how to achieve any cryptographic task computationally without also getting EFI, and this is due to recent results. Like the last hole was plugged by Korana and Tomer in a paper that I think was posted just 2 weeks ago. This is sort of the evidence that we have, but we don't have like a sort of a formal reason yet as to why, if and why this would be essential. And we don't know of a separation from pseudorandom states. We know there's a derivation in one direction, but we don't know what's going on in the opposite direction. So we can do cryptography even if one-way functions do not exist. This is great. The next thing that I wanted to talk about was pseudorandom unitaries. I'm just going to mention it briefly, mostly for the sake of the open problem in the end. So you can think about pseudorandom quantum states, but you can also think about pseudorandom quantum operators. And quantum operators are unitary operators in general. And just as you would want a quantum state that's indistinguishable from a random quantum state, you could want to get an efficiently computable quantum operation that's indistinguishable from a random unitary. And there are candidate constructions, but there's none with a proof. So we don't have a proof under any assumption. So that's a very good open problem for the brilliant young or not young researchers and students that want to work on it. The next thing that I want to talk about is pseudo-entanglement. In this case, we take our quantum system and sort of split it into 2 parts. So we have 2 subsystems, A and B. Each one of them has n/2 qubits. And entanglement is these quantum correlations between these 2 subsystems. And entanglement is a very fundamental notion in quantum information and quantum computing. Almost all the applications that we have use entanglement. If you want spooky interaction at a distance, you need entanglement, and many other tasks. Shor's algorithm, but really almost everything. Teleportation. The most basic entangled system is this very simple EPR pair. So this is a 2-qubit system, and it's just sort of a superposition of the all 0 state. So it's over 2 qubits. So it has 2 parts. Each one is 1 qubit. And it's a superposition of like the all 0 state and the all 1 state. And this state is maximally entangled, which means that it has the most entanglement that it can have. I'm not going to go too deep into what this means, but I just want to mention this monogamy of entanglement property, which means that if 2 states are maximally entangled with each other, then they cannot be entangled. Each of them cannot be entangled with any other quantum system. So this is a useful property. Now, there are many ways to quantify entanglement, which is not a good thing because for every application, you need to figure out what works for you. A popular one is to use entropy. So you can use the negative of the conditional entropy between the 2 subsystems, A and B. And this entropy measure that we use is the von Neumann entropy, which is a quantum extension of Shannon entropy. Notice the minus sign. So if systems are entangled, then this von Neumann entropy can be negative. And this means that the systems are actually entangled. So negative relative information, relative entropy, means that the 2 systems are entangled. And physicists refer to this von Neumann entropy as entanglement entropy. Well, yeah. Good. So the task of pseudo-entanglement is to create systems with low entanglement. So systems where they have subsystems A and B that don't have much entanglement with each other, but are computationally indistinguishable from ones with high entanglement or even maximally entangled quantum systems. And you can show that you can do this using pseudorandom states or other techniques. So there are actually works that show this, and we'll see why this is interesting. I want to mention like a recent work where we tried to consider a different notion of entanglement measure. We wanted to think about sort of operational pseudo-entanglement. So rather than sort of looking at this, I don't know what to call it, analytic notion, you're actually thinking, how many EPR pairs do you need in order to construct this sort of bipartite state AB? So A and B start by just sharing a bunch of EPR pairs, and they work locally, and they can communicate classically, and you need to create a quantum state. How many EPR pairs do you need in order to complete this task? And you can also think about the opposite task, entanglement distillation, where you start with your state and try to get, by local operations, as many EPR pairs as you can. And you can define pseudo-entanglement with respect to these measures, and sometimes this is also interesting. Okay, so let's move on to applications. Anybody knows what this is? Right, it's a black hole. So this is a Sagittarius A star, which is the black hole in the center of our galaxy, the Milky Way, for those of you who are from different galaxies. Do you know why it's called Sagittarius A star? What the star stands for? So as far as I understand, when astronomers come up with an exciting discovery, they mark it with a star. So A star just means that it's an exciting, radio source or whatever it is. So, astronomers they have, I guess, thousands of years of experience in naming things. So they're probably pretty good at this. So that's a cool naming convention. So yeah, we're going to talk about black holes. But before that, a little bit of a disclaimer. So, I'm a TCC person, just like you. I'm not a physicist. So this means that if you there's a bunch of physics questions that I'm not going to be able to answer. But the good thing is I'm going to be able to give us sort of our perspective on these matters. So I'll do my best. So what I want to talk about is first is black hole radiation and complementarity. So let's see what that is. So let's start by talking about black holes. We've seen a real black hole, but here's an illustration, which is, I think, at least as nice. So in classical gravity, which is general relativity, so a black hole is just a region of space-time. This is true still also in the quantum regime. So we used to think, some people are used to thinking about black holes as an object, but it's not. It's just a region of space-time where if information gets in, where whatever goes in there, any information that goes in cannot come out. You can schematically think about the black hole as having, a singularity in the middle. So there's like very strong gravity in the singularity. You don't want to go in there. And the boundary of the black hole is called the event horizon. And this is essentially the line where if you cross it, you can never go back. And the region of the event horizon doesn't necessarily have very strong gravity because it can be very, very far from the singularity if the black hole is big. So this is how you should think about it. Like around the event horizon, things seem normal. If you go too close to the singularity, and an illustration of a book going into a black hole. Good. Information goes away. It goes into the black hole, it never goes back. However, I think pretty surprisingly at the time, in the late 70s, Bekenstein and Hawking actually showed that black holes should emit radiation. If you analyze sort of the region of the event horizon quantumly, then you see that radiation is supposed to come out of it. It's called Hawking radiation. And this means that the black hole is going to evaporate eventually. So it's if you just take a black hole and leave it be, it's going to start radiate and radiate and radiate until after like gazillions and gazillions and gazillions of years, it's going to evaporate. This is very weak radiation, so we cannot measure it. So we only have theoretical evidence that it exists, but I think everybody's pretty sure that this is actually like something that happens. And now you already have a conflict with general relativity, because general relativity says that nothing can come out of a black hole, but actually, radiation does come out, and in the end, the black hole is going to evaporate. So what happens to all the information that goes in? I think the consensus now, or near consensus, is that the information is going to come out eventually. So the entire evolution of the universe is unitary, and therefore information at the level of the universe, information never gets lost. So if it goes into the black hole and the black hole radiates, then the information is supposed to come out in some way. And now we need to think about this information in the Hawking radiation and what its properties are, once we establish that in some sense it has to contain the stuff that was thrown into the black hole. So naturally, it's not just going to be like the black hole throwing the book back at us. It's going to be encoded in some way, and the encoding actually matters. And I should mention that usually the way black holes are modeled as, so it's known that black holes are supposed to mix information very rapidly. So information that goes into the black hole sort of gets smudged all over very quickly. And it's actually usually modeled as a random unitary, but we know that it can't be a random unitary because the universe, well, it should be computationally efficient. So this sort of brings us back to this notion of pseudorandom unitaries that I mentioned before. Pseudorandom unitaries could be like also interesting in the study of how the real implementation, how the universe really implements black holes. So that's just leaving it out there as an additional motivation. So again, thinking about the entropy that is contained in the Hawking radiation. So we already sort of try to think, we're inclined to think that it's encoded in some hard way. So one thing that physics tells us, or tells the physicists, is that any information that's emitted in the radiation should be entangled with information that remains in the black hole. So that the radiation that goes out is actually maximally entangled with other piece of radiation that actually goes back into the black hole. So what goes out needs to be maximally entangled with the stuff that's inside. On the other hand, it should also be entangled with all the radiation that was emitted previously. So if the black hole is old, then it means there's a lot of radiation that's already come up, that already came out sort of in the history of the black hole. And once the black hole gets small enough, there's no sufficiently many degrees of freedom inside the black hole to be entangled with everything, so it needs to be entangled with the outside. And that's a problem because we mentioned the monogamy of entanglement property. So a quantum system cannot be entangled with two different systems. So you cannot have the outgoing radiation being maximally entangled both with the inside of the black hole and with the outside of the black hole. So that's a conundrum. And it was solved it's attempted to be solved in a very creative way. So they're saying, well, it seems to be entangled with two things. One of them is inside the black hole. One of them is outside the black hole. They're sort of pretty disjoint from each other. So maybe they're just not two different things. Maybe it's just the same thing. It's two manifestations of the same sort of quantum system. And if you're inside the black hole, then you see it in one way. And if you're outside the black hole, you see it in a different way. But actually, it's the same thing. So it's mind-blowing, but not as mind-blowing as we will get. So this is sort of a prominent idea on how to handle this sort of radiation paradox.
Can I ask a question, Zvika?
I don't know. It depends on the chair.
Yes.
Okay, then I'll ask two.
You already wasted.
Wait, I didn't approve.
I don't. First of all, I don't understand why does it have to be pseudo-random and not random? Why can't the universe be truly random? I missed that.
Oh, because truly random just has exponential complexity, just like in the classical world, right? You don't expect real random functions to exist just because they have an exponentially long description. If the universe is efficient, I mean, it needs to be polynomial in the length of the history of the universe.
You believe the Church-Turing thesis for the universe?
In this room we do.
Okay, and my other question, if it's two manifestations of the same system, is that related to cloning? Is it like?
Right. So you can think about monogamy of entanglement and no cloning as very related to each other. So you could think that you actually sort of clone that. You can also think about it's a violation of no cloning, even though it's not like you're taking a generic state and cloning it. But it's fine. It's a very similar intuition, so it's good to think about it in this way. Okay, good. But we want to talk about cryptography. So let's see what happens next. So Al-Mihir et al. Actually were not satisfied with this answer, and they actually proposed an experiment where one can actually sort of see this monogamy of entanglement. So the whole point is that these two things are the same system, so you should never be able to sort of witness the two copies side by side. And they proposed, so this firewall paradox is not really a paradox, it's a thought experiment. And what they're saying is someone sits outside, it looks at the history of the radiation, it takes out of it, it's like sort of computes out of it the piece of information that's supposed to be entangled with the next thing that's supposed to come out. It sees that you're fully entangled with this thing that comes out, and then you jump inside and find like the black arrow that matches, and then you see that these two things are actually you witness this violation of the monogamy of entanglement. And this is not good, and therefore they suggested that the event horizon maybe should have this firewall, which is a very high energy barrier that prevents these black holes from existing. But I think a lot of physicists don't like it because they really want to think about event horizon as an area that is sort of tame. It doesn't have high gravity. There's no reason that firewalls should appear there. So they really want to try to salvage this sort of complementarity without using firewalls. And Harlow and Hayden had the following proposal. They were saying, look, in order to conduct this experiment, you actually need to take this historic radiation and decode it. And that could be a computationally hard task. And then they gave some toy model where decoding the radiation is SDK hard. And Aronson showed that you can actually use injective one-way functions. So you can actually use cryptography to create like toy decoding problems that are hard. And bam, problem solved. We don't need to worry anymore about the firewall paradox. Except like, this, how is that even a thing? That sounds crazy, right? Like, there's an experiment that could in principle happen, but we're saying that because it takes a lot of computational resources, then we can just disregard it. The point was that, you know, if a sufficient amount of time passes in the decoding process, then the black hole will evaporate, or this black arrow is going to reach the singularity and be out of our reach, or something is going to happen that's going to save us from actually seeing this violation of monogamy. But this really sort of hinges on us sort of being unsuccessful, like taking a long time in running this decoding task, which seems unsatisfactory. But it's actually not very foreign to the way sort of the physicists think about these things. So they have this invention that's called effective field theory. So they realize that they cannot sort of get a theory that works at all energy scales. So they can come up with you know, these field theories that work in regions that have fairly tame gravity, and they can come up with pretty accurate theories that actually sort of say everything that's going to happen there, but they actually tell you nothing about what happens in high energy, like in high gravity or something like this. The theory is not going to say anything about it. And this is a good thing because it allows you to sort of analyze these regions without having a theory of quantum gravity. But it's also a bad thing because you want to learn something about quantum gravity. It also means that, you know, if you don't get to these high energies, then you're not going to be able to learn anything about quantum gravity. And, you know, the universe didn't have to be this way, but it appears that at least, you know, in some cases it is. So they're pretty okay with saying, you know, some things you can have a theory that works very well, but when extreme things happen, it just stops working, and that's fine. Like sometimes the universe just hides from us what happens when extreme conditions happen. And then they're saying, okay, so solving intractable problems in less time than you're supposed to should also count as outside the regime of applicability of this effective field theory, and then maybe it's okay. So this is their rationale. So this is sort of a way that I think it's still considered a way to resolve this paradox. Very recently, we were able to show that actually it's not only that you can use sort of cryptography, like injective one-way functions, in order to create these hard-to-decode systems. There's actually an equivalence. So if you define the problem properly, having, like, again, a toy black hole that creates radiation that is hard to decode is actually equivalent to the existence of quantum commitments to classical bits, or these EFI pairs that I was talking about. So, you know, if we have these quantum commitments, then we can create hard to decode black holes, which is good. It's similar to what was known before, but actually the opposite is also true. So if there exists like black holes that asymptotically, you know, emit radiations that is hard to decode, then you also have quantum commitment schemes, which I'll talk about a little bit more later. But just sort of the basic idea. So in hindsight, it seems a fairly natural connection, because the black hole sort of emits this information. The information exists inside the radiation. It's fully determined, but it's inaccessible. So this should remind you of a commitment to this quantum information. So the black hole really, whatever it emits, it has to be a commitment to this quantum value, to this quantum information that is being emitted. And we can get quantum commitments from classical commitments. Quantum commitments to quantum values from quantum commitments to classical values. And this is sort of what we do here. But this sort of brings us to a more philosophical question of whether we can sort of try to use this sort of things as getting some additional justification to the existence of cryptography. So why do we think, so usually when we think about cryptographic assumptions, why do we think that they're hard? Well, you know, we rely on our intuition, insight, experience. A lot of people tried to factor for a very long time and weren't successful. So why don't we sort of think about this as a cryptographic assumption? If we're lucky, we also have this win-win paradigm that, you know, if it's not, then we have a new algorithm. So that's a good thing. But you can think about an alternative approach, sort of very naively and schematically. So first, map out all the laws of nature. So do science and figure out exactly how the universe works. And then, you know, find a process that sort of can be carried out efficiently, but is hard to invert, and use that as your one-way function. So again, so this is very naive, but you can try to do this. It's somewhat different. It's not going to give you like a proof, because whatever model you have, whatever laws of nature you have, it's just a conjecture. You never know that it's actually the real laws of nature. but it's different somewhat from the previous approach in terms of methodology, because in order to deduce the laws of nature, you do experiments and you do observations, and this is at least sort of a different path from the way that we normally think about creating cryptographic assumptions. So this sort of black hole thing is, you could think about it as an example, sort of, even though it's all like thought experiments and not experiments you can actually conduct currently. But it can give you some sort of independent evidence. So it's a different path that shows that cryptography could actually exist. So I think that's pretty cool. Of course, it's debatable. Good. So I want to actually give you another example of where cryptography is used to save complementarity. And this is the ghost in the radiation. So this is a paper by Kim Tang and Preskill. And they were thinking about another aspect of this complementarity thing. So we're saying that the stuff inside and the stuff outside should actually be the same system. So if I want to communicate with someone inside the black hole, can't I just do it by sort of communication with the communicating with the radiation? So sort of you can think about the ghost of the person inside the black hole actually living in the radiation, and you can maybe interact with them. And that should not be doable. But again, sort of the approach that they take is to use pseudorandom states to argue that anything that you do to the radiation, you cannot do anything meaningful to the radiation that will sort of affect in a meaningful way what's going on inside in the system inside the black hole. And so they showed one direction. While I was preparing the slides, I realized that there's an open question here, whether you can show, again, sort of an equivalence, that it has to be the case, that it maybe, more pinpoint the cryptographic object that you need here. So that's another angle on this. Okay, and I want to switch to the next thing that I want to tell you about. So this was black holes and where cryptography comes up in that regime. Now I want to talk about holography and the AdS CFT dictionary. Okay, big words. Let's see what those are. So what is holography? Holography is this principle that says that everything that happens sort of inside some region is in some sense determined by the boundary. And actually this phenomenon also happens in black holes. We didn't talk about it before, but you can actually think about all the information of the black hole actually being concentrated around the boundary. It's well known that, in terms of physics, it's well known that the entropy of the black hole is proportional to the surface area of the black hole and not to its volume, which is, so holography is counterintuitive, right? If you think about a black hole, it has some volume. And if you want to try to sort of pack information, like let's say I have some region with some volume and I want to try to pack information into that region. So I'm just going to take like a bunch of hard drives and I'm just going to sort of, put them one next to the other in this thing. And this is going to scale according to the volume of the region. But it turns out that if you try to like squeeze things as much as you can, in the end, you're going to sort of create a black hole, and you can actually not store more information than the surface area of the boundary of the region, because the black hole is the region. Has the maximal entropy of all possible regions in space-time. So this is just to say how holography is sort of sometimes counterintuitive principle. It sort of collides with our notion of locality that things should only affect what's near them and not be affected by like something that's happened on the outside. But it's a hot topic. And in particular, there's this AdS CFT correspondence that was introduced by Maldacena in '97. It's probably the most researched concept in high energy physics. I think I checked, the paper has like 24,000 citations. Yeah, everybody works on AdS CFT. And now we will know what it is also, at least in broad terms. So we consider a universe. Why not? Why not consider a universe, right? That's what we do all the time. And this universe has AdS geometry. AdS means anti-de Sitter. This is like hyperbolic geometry for those of you who are differential geometers, which I'm not. But it has some geometry, this anti-de Sitter geometry. And for such a universe, you can actually sort of describe them as like this cylinder. So at every slice in time, you can put this anti-de Sitter space into like a circle, and then you have time evolution, and the time evolution actually creates this this cylinder. So this is so the cylinder is the universe. And if you think about the cylinder, then it actually has the boundary, like the surrounding of the cylinder, and this is a conformal boundary. For us, it's just a name. So the inside of our universe, it's called the bulk, and that's the universe with gravity. So it's so in classical physics and general relativity, gravity corresponds to curvatures in space-time. So the inside the bulk is allowed to have this has this curvature. But the boundary actually has this flat geometry, so there's no gravity on the boundary. And why is that a good thing? Well, this AdS-CFT correspondence, so CFT stands for conformal field theory. And it says that if you want to do physics with gravity in the bulk, like you have a physical theory that describes what's going on, like a quantum gravity theory of the bulk, then it's going to be dual to some physical theory on the boundary that does not have gravity. So CFT is conformal field theory, so you have a conformal field theory on the boundary, and this one does not have gravity. So I think in the original Maldacena paper, this was shown for some string theories. So again, it's a theory. It can be shown in some models. I don't know how far it can be extended. It's also worth pointing out that our universe does not seem to have AdS geometry. But you know, why let that stand in our way? It's still a cool property that allows physicists to study quantum gravity. So you know, why not you know, take advantage of it, see what we can learn from it, or they see what they can learn from it. So the hope is that to do physics without gravity is potentially easier. This is something that physicists know how to do pretty well. So you're just going to do this physics without gravity on the boundary. You're going to derive from it the physics with gravity, the quantum gravity theory in the bulk, and bam, you solve quantum gravity. We can all go home. So this is a pretty nice plan. You know, they do need to figure out first what is the correct CFT theory that lives on the boundary, and then also how to translate from the states and operators that you can apply on the boundary to the states and operators that live in the bulk. So you know, the point is that if you want to know, if you want to run an experiment in the bulk, you should be able to sort of maybe translate it into the corresponding state of the boundary, run it or you know, do your calculations on the boundary and then translate it back, and then you'll know what happens in the experiment in the bulk. So yeah, so it's challenging. There's a lot of work that's being done to try to better understand what is going on there. And here actually cryptography is spoils the party a little bit. So we can think, so there's various ways where crypto can spoil the party. I'm going to describe like this general template. So think about the following thing. On the boundary, think that you can have two different states, psi1 or psi2. So you can think about a boundary that has psi1 or a boundary that has psi2. And let's think about the geometry on the AdS that you have that corresponds to these boundary states. So each one of them corresponds to potentially a different geometry. But you know, geometry is something that you can see sometimes. So you can have an operator like measuring tape that you can use in order to sort of distinguish these two dual geometries, right? So you're just going to go and measure and see if you're the first one, then you're going to do one thing, and if you're the second one, you're going to do something else. And this will allow you to distinguish these two geometries. And again, you have the inverse dual mapping. This means there's also an operator in the CFT region that has these properties. So why is that a problem? So it could be a problem if we have certain conditions. So first of all, we want to if we can generate these psi1 and psi2 such that they're computationally indistinguishable. Let's say computationally indistinguishable even to quantum computers. but they're still legal CFT states. So not all states are legal. I guess there's a whole theory behind it. But there should be legal CFT states, and yet the geometry they induce is different and can be distinguished sort of in the bulk, in the ADS part. If this happens, then you seem to run into a problem, right? Because so somehow quantum gravity allows you to distinguish between these two states. Because what you're going to do is you're going to go to the ADS. You're going to use your measuring tape, and this is going to tell you whether your boundary state was the first one or the second one. So this gives you a distinguisher between these two possible states. So if you can generate such states, then this sort of quantum gravity could allow you to solve intractable problems and violate the quantum extended Church-Turing hypothesis. So quantum extended Church-Turing means that anything that can be computed in the universe can also be computed by a quantum computer. So yeah, that could be a problem. And you know, one way to go is to say, yeah, well, quantum gravity maybe is a new computational model. Maybe we have a new tool now, and we need to learn its complexity and so forth. But the more pessimistic and probably more realistic point of view is to say that in order to construct this distinguisher that I was mentioning, you actually need to be able to compute these mappings, the mapping between the either in one direction or in the other direction, or both. You need to be able to compute these mappings, and probably this is what's computationally intractable. So all these things can be true, but still, if this dictionary, the mapping between ADS and CFT is hard, then the quantum Church-Turing hypothesis is not broken. But you know, it's tough luck for us, because like this whole way of trying to do physics by working on the boundary and then mapping it into the bulk might have a problem to actually be useful. Like if you actually want to use it, you might run into like hard computational problems. And yeah, that's a conundrum. So it's important, interesting to see whether this can actually happen. And I think people think that it usually should not happen. Like if your ADS geometry is like nice, then things should also behave nicely on the boundary. But in some cases, it could be the case. So there's this work by Boland, Pfefferman, and Vazirani that sort of relate. So now they're using pseudorandom states, but they work really hard to show that you can actually come up with a construction of pseudorandom state, or at least conjectured construction of pseudorandom states that can actually be generated in the CFT on the boundary. So whatever people think of the boundary, it allows you to generate these pseudorandom states. And they're related via some conjecture to some surface area of stuff that's going on inside a wormhole. And in that regime, they're able to sort of show that in some cases you're going to have high complexity of the dictionary, or breaking a cryptographic assumption. The works that I mentioned before in pseudo-entanglement are also related because again, sort of the, I guess, widely believed conjecture is that surface area in the bulk is actually related to the entropy of the corresponding region in the boundary. So if you have a region in the boundary and the quantum state on this has some entropy, this is actually going to determine the volume or the surface area of some section, properly defined section in the bulk. So studying pseudo-entanglement is sort of, again, a way to try to sort of tap into cases where you'd have states that are computationally indistinguishable, but correspond to different geometries, in the bulk. So this is a little bit, the first work is more sort of inclined towards this goal. And finally, I just wanted to say that in order to conduct this experiment, it doesn't necessarily mean that we need to live in a universe where ADS-CFT holds. It's quite possible that we can think about an imaginary universe that has ADS-CFT correspondence, but so long as we can simulate this universe, right? So long as we can, in our universe, sort of simulate this ADS universe and see what comes up there, we're still going to be able to generate a distinguisher. So it's possible to sort of argue. So it's meaningful to argue about this, even if this is not our universe. I'm going to wrap up. Yeah. So good. Good job, everybody. Quantum TCC rocks. Everybody's doing a great job. We have like great achievements, and we're going in very interesting directions. We're creating privacy and security tools for this quantum future. At the same time, exploring the mysteries of the universe, coming up with interesting ideas and observations. That's great. We're not done yet. There's more work to be done, both conceptual and technical work. And yeah, we need to do it. So thank you very much.
Thanks a lot, Zvika. So we have time for some questions.
So you assume that the black hole dynamics is pseudo-random unitary. So if you already have pseudo-random unitary, this also implies EFI, and pseudo-random unitary is stronger than EFI. So why you want to construct EFI?
So if I understand the question, so in this black hole, the hardness of black hole decoding, we don't assume anything about the black hole dynamics. So all we're saying is that if the black hole dynamics, whatever it is, creates a hard to decode radiation, whatever it can be a pseudo-random unitary, we don't know. You're right that if we understand the black hole dynamics, then maybe we don't need this correspondence because we know exactly what is the radiation that is emitted. But we can say, even if we don't know the dynamics at all, if it emits radiation that is hard to decode, then it gives you a commitment scheme. And if there exists a commitment scheme, then at least it's plausible, or at least it's possible, at least in some toy model, there could exist a black hole that emits a hard to decode radiation. So, it doesn't excuse us from actually studying the black hole dynamics. It just says that we can sort of try to speculate some of its properties even without knowing what the dynamics are.
So hardness of decoding is weaker assumption than the pseudo-randomness of black hole dynamics.
I think so. I mean, I didn't think about it thoroughly, but from our little discussion, I would think that you can say that. Yeah.
Thank you.
Okay. I'm gonna let Guy manage it.
Yeah. So you were saying that it's somehow like this black hole theories give us, if they're correct, they should give us cryptography. Do like the specific proposals of how black holes work give us candidate constructions of commitments and cryptographic schemes? Or?
I like the question. I'm not sure what the answer is. So this is actually sort of to relate to the previous questions, right? If you're doing something that's pseudo-random, then it makes sense that it's going to give you something that's perhaps not very satisfying. It's not clear if it needs to exactly be a pseudo-random unitary because there's no place for the seed, right? Like all these pseudo-random objects actually have a seed. And in like, if you think about black hole dynamics, then you're supposed to know all the laws of nature. So I don't know where's the place where you plug in the seed for this pseudo-random unitary. So I don't even know how to frame this model. But yeah, it's like I think it's a very interesting sort of direction to try to study.
So you mentioned the relation with the classical one-way function primitive. What about what do we know about the relation with the classical P versus NP question?
Okay, so there's this, I think, a whole different branch. It's not different, but there's this whole branch of trying to understand how one should think of quantum complexity theory. And again, I'm not like a super expert, but I can tell you sort of that my angle on it. So it seems like there's a lot of a lot of quantum tasks that cannot be reduced to a classical parallel. So this sort of the complexity class hierarchy, even quantum classes like QMA and BQP, they still think about deciding a language or computing like some classical function. And when you're talking about quantum functionality, then it's not clear that like all of this structure is even suitable to study these things. And there are some ideas on sort of how to define classes where you have quantum inputs or quantum outputs. In particular, one important open problem that I didn't mention here is whether EFI exists even if P equals P space. So we know that in this case, like if P equals P space, then P equals BQP. So that's fine, but it still doesn't resolve the question of whether you can have quantum cryptography. So was that the question?
Yeah. Thanks.
Yeah. I had one question. You said, I think at some point, and I may have completely misunderstood this, but that basically you cannot manipulate, sort of, if we think of our black hole as a pseudo-random generator, we cannot manipulate the output by feeding more things into the black hole. But I think you also said that sort of the black hole's computation or the seed is sort of just polynomial in the length of the universe, or whatever has been fed in the past. So even if I feed in something, you know, like that is, if I take as long as if I wait as long as the lifetime of the universe up to now and feed in, like, if I double the amount of information that is in the inside the black hole, I still cannot manipulate things or manipulate the output or bias the output.
So I was talking about like a very like the simplest scenario, which is that nothing goes into the black hole. Stuff only comes out. So that you take a black hole and let it radiate. I think there are some, you know, thought experiments and suggestions on trying to sort of get to more interesting circumstances by putting things inside and seeing what happens. Was that what you're?
Yeah, I thought you had some slide where you said I cannot manipulate the output by feeding more things inside, but I may have understood.
Oh, yeah. So maybe I maybe it wasn't clear. So what I was talking.
Okay.
So this was the ghost and the radiation slide you're talking about.
Maybe.
Okay. So so let me say again something that I did say. So you can say if you have complementarity and the outside and the inside are the same thing, and let's think about sort of your friend going into the black hole, or I don't know, not friend, going into the black hole to explore. Then you might want to then you may be able to communicate with them by sort of interacting with the radiation that's already outside. And what this work of Kim Tang and Preskill says is that you should not expect to be able to do it if you're an efficient process.
Last question, I think.
So, so we think of simulation as a thought experiment, right, for security definitions. So is there any reason to not have simulation which is not physically realizable, right? A simulator lives inside some black hole which can violate non-cloning and so forth. You know, would it make sense to think of that?
So violating no cloning, it's not that, okay, so this no cloning thing, it's not that it's like, it's an operator that's not permitted. It's actually, it's not even well defined in quantum information theory. So it's just something, but I think you were saying something, you were referring to something somewhat different. So you're saying I can just write down this.
Yeah, you can copy the entire, you know, state. You can.
Sure. Yeah. If I actually write this exponentially long state on paper, then I can clone it in the sense that I can take this classical description and copy it. So long, if I have like a classical description of what's going on, then I can sort of copy it, but it's still not going to allow me, to duplicate a physical system.
So I guess my question is there a safe way to define like an imaginary world where in some boxes, quantum physics is all violated, but still it's good enough for a thought experiment to say this is secure. Right?
So yeah, so I think you can. I'm saying that you need to be careful because like the frame of reference really matters. Like it's not physical. It's not a physical process like cloning, but you can say that under some, again, definition of like a classical description of the system, what do you mean by duplicating quantum state? Sorry, it doesn't feel like a very satisfying answer. We can talk about it later if you want.
Yeah, let's thank Zvika again.
Thanks.
And we can all talk about black holes over lunch. It's in the usual place, I think.